Hey there, Mr. Sutton here with the AB Calculus 412 Part 2 homework solutions on motion. For this problem, we have a particle moving on a straight line with a velocity given by v of t equals 7 minus 1.01 to the negative t squared is what that says. And time is going to be a positive or zero number. We want the acceleration of the particle at time 3. Well, since we've already got the velocity, and the acceleration is just the derivative of the velocity, we just need to find v prime at time 3. So we're just doing v prime of 3. Now this is a calculator question, so I just need to put the original function in Desmos, and then I can go from there and pretty much literally just write this and get the answer. So back on Desmos here, we've got v of t equals 7 minus 0 or 1.01 exponent negative t squared. So we've got exponents inside exponents here. And then I'll go down to another entry and I'll just do v prime of 3. And that comes out to about 0.055 if I round that off to 3 decimals. So that's going to give me choice B. For this problem, we have a particle moving along the x-axis so that the position at all positive times is given by x of t, which they're not telling us, and dx over dt, so x prime basically, which is this polynomial function. And they want to know the acceleration of the particle. They want to know when the acceleration of the particle is 0, at what time. So strategy on this one, we need to figure out a formula for x double prime of t. We've already got x prime, so we just need one more derivative, and we just need to see where that equals 0. Given the calculator nature of this, we're just going to put that on Desmos once we figure it out. So x double prime then, using our power rule, we're going to have negative 40 t cubed, and then we're going to have 18t, so plus 18t, and then plus 8. And again, we're seeing where this equals 0. So on Desmos, let's put that on there. So I'm just going to call this a of t, and that's going to be negative 40t cubed, and then plus 18t plus 8. And they didn't give us an exact interval other than all positive numbers. So let's just find where we're crossing the x-axis here. It looks like we've got a nice spot here at about 0.831. So we'll just write that down. And looking at my answer choices, we do have that for an answer choice. So let's pick choice B. For number 3, position of a particle on a straight line is given by this function here. We want to know the acceleration of the particle at time 4. So for acceleration, we need the second derivative of position. First derivative is going to be s prime equals 2t plus 4. And then second derivative of that, s double prime, is just going to be 2. Now we want to know the acceleration at 4. This is a constant function that always comes out to 2. So 4 and everywhere else, this thing has an acceleration of 2, so choice B. For this problem, we have a particle moving along a line, so its velocity is given by this v of t function. We want to know at what values of t is the speed of the particle increasing. So the idea with speed is if the sign of the velocity and the acceleration match, then the speed will be increasing because they're working together. If the velocity and acceleration signs are opposites, then the speed will be decreasing. So we basically need to figure out when this and this v function and its derivative have the same sign. Now to do this, I need to figure out where they're crossing the x-axis, or the t-axis, I guess. And then I can just kind of graph them out and go from there. Well, actually, I'm going to graph them first to figure that out, but I'll graph them both at the same time eventually and compare their signs. So let's figure out where v of t equals 0 as a starting point. So let's go to Desmos. So let me put in v of t, and that's going to equal negative t to the third plus 2t squared plus 2 to the negative t, so that's a little bit weird, but hey, we'll roll with it here. So there's that function, and just clicking this, it looks like 2.057 is the only intercept for that one. So we're going to keep track of that. Next, I need to figure out the acceleration, or the v prime. So that's going to be negative 3t squared, using my power rule here, and then the plus 4t. And then for this last one, we'll have negative 2 to the, well, actually, we'll have 2 to the negative t, but we have to multiply that by an ln of 2. That's the exponential rule. It's the base to the exponent times the ln of the base. And also we have to take the derivative of negative t, the inner function, so that's all going to come out to negative 2 to the negative t, ln of 2. So a little bit tricky on that last one. All right, so let's graph this out and see where this thing equals 0. So back on Desmos, let me move this so I can actually see that function. And whoops, let me get that back. There we go. So let me call this a of t. So negative 3t squared plus 4t minus 2 to the negative t, and then ln of 2, all of that. And then moving that up so I can see it a little better and zooming in, we've got 0.177 and 1.256. So both of those spots there. All right, let me put a picture of what I've got on my graph just so we can look at it. This top function here was v of t. This bottom purple one here was a of t. And my three intercepts that are going to come into play, we've got 0.177. This one here is about 1.256. And this last one is the 2.057. And again, I'm trying to figure out where v of t and a of t have the same sign. So taking a look here, when we first start at 0, a of t is negative and v of t is positive, so that doesn't count. Once we get to 0.177, they are both positive for a while, and then a of t ruins it by going negative again at 1.256. So at the very least, they have the same sign on the interval from 0.177 to 1.256. Now, at some point, v of t decides to join a of t in negative territory, and that happens at 2.057, and it continues actually, if you look back at Desmos, that's going to keep going on forever and ever and ever and ever as far as we zoom out here. So we'll go to infinity with that interval. Since they have the same sign on these two intervals, that means our particle is speeding up on these intervals, giving us choice E. For this calculator-based problem, we have a particle moving along a line so that at time t, between 0 and pi, the position is given by this s of t function here. We want to know the velocity of the particle when its acceleration is 0. So we need to find a few things in this problem. First, we need to get the velocity, firstly so that we can then find the acceleration. Secondly, so that when we figure out where the acceleration is 0, we can plug that time back into the velocity. So let's start with velocity. That's going to be s prime of t. So going term by term, we're going to have, this will be, let's see, cosine's derivative is negative sine normally. So this will be positive 4 sine of t. Minus, using our power rule, 2 times 1/2 is just 1, so just minus t. And then that plus 10 is just a 0 if you take that derivative. All right, so we're going to go back and use this v of t in a moment. But first, let's get a of t. That's going to be v prime of t. And that's going to be, let's see here, 4 cosine of t minus 1. So at this point, we're going to figure out where this acceleration equals 0, and we're going to go to Desmos to do that. So here I am on Desmos. While I'm entering things in, I'm going to enter in the velocity because I know I need to plug something into that in a little bit. So let me do v of t equals 4 sine of t minus t. That's an interesting function. I don't need to graph it though. What I do need to graph, and I'll enter this on my next level, is a of t, my acceleration. That's going to be 4 cosine of t minus 1. So here's that graph that we're looking at. And they specify the interval between 0 and pi. So going back here, I'm going to change my interval to be from, we'll just do 0 to pi. So 0 and then pi. And I'll make my steps go by, well, let's just do pi over 2, just so I can get a good picture of where this thing is ending. All right, there we are. So there's only one place where this equals 0 on this interval, and that's right here at this spot at about 1.318. So I'm going to copy that because I'll probably need that value in a moment. Let me just write down what I've got here. So there was my picture. We said that acceleration equals 0 at time 1.3181 if we want to take it out a few decimals. And so now we're going to plug that back into v because we want the velocity at that spot. So let me go down an entry level, and I'm just going to do v of, and I'll now copy and paste what I just got into there. And that's coming out to about 2.555, or just 2.55 because all the answer choices have only rounded to 2 decimal places here. So we'll just go with that, and that's going to be choice D.
For this free response problem, we have an object moving along an x-axis with an initial position of 2, and velocity is given by v equals sine of pi over 3t. Based off of this, part A, we want the acceleration of the object at time 4. Well, acceleration is just going to be the derivative of velocity. So that's going to end up being, let's see here, we've got cosine of pi over 3t times a tail of pi over 3. So that's what this looks like. And then we just have to plug in 4 to find the acceleration at time 4. So that's going to look like this. We're going to have 4 pi over 3 inside here if we plug 4 in for t. Now you can actually leave it like this. This is numerically equivalent to whatever the answer is they're looking for. You should just stop here and be done. But if you just can't leave well enough alone, let's go ahead and simplify this. So this is really, let's see, I think better in degrees. So this is really 240 degrees, which has a reference angle of 240 minus 180, so 60 degrees, and cosine's negative in quadrant 3. So this is essentially negative cosine of 60, which is negative 1/2. So we've got pi over 3 times negative 1/2, which comes out to negative pi over 6. For number 7, position of a particle is given by this function here. We want to know when t is pi, what's the acceleration of the particle? So if we have position, we need 2 derivatives to get acceleration. So x prime, first derivative, that's going to be 2 cosine of 2t plus 3 sine of 3t, using a little chain rule in there. X double prime, acceleration now, that's going to be, let's see, this is going to be negative 4 sine of 2t, and this is going to be plus 9 cosine of 3t. So we just need to plug pi in for all of these. So if I go ahead and do that, we've got sine of 2 pi, that is 0. So that just zeroes out the first term. Cosine of 3 pi, well, this is like having cosine at 1 pi. So that's going to be negative 1 times 9 is negative 9. So then negative 9, choice E.
For this calculator-based free response problem, we have a particle moving along the x-axis with a velocity given by this v of t function. So I have a strong suspicion I'm going to need to use this function, so let me immediately go to Desmos and just enter that in there so that I have it. So v of t equals negative parentheses t plus 1 times sine of parentheses fraction t squared, and then put 2 down there, and close that fraction, and boy is that a lovely looking function. We'll come back to that. So they also tell us that at time 0 the particle is at position x equals 1. Cool. Okay, so they want us to find the acceleration of our particle at time 2, and then answer the question of whether the speed of the particle is increasing at time 2 with justification. So let's do the acceleration first. Acceleration is the derivative of velocity, so I can find the acceleration at time 2 by just doing v prime of 2. So that'll be my thing that I'm doing on my calculator now. Let me go back to Desmos. Since I'm just taking the acceleration at a single spot, I can just do v prime of 2 without actually showing what the acceleration looks like as a function. So there it is. We have a value of about 1.588 8. Okay, and they didn't give us units for any of this, so we don't have to give them units. So there. All right, now they want to know the speed. In order to figure out, or they want to know whether the speed is increasing or not. To figure out if we're speeding up or slowing down, we need to know both the velocity and the acceleration and compare the signs of them at time 2. If the signs agree, then we're speeding up. If the signs are different, then we're slowing down. So I've already got the acceleration at time 2. Now I just need to find the velocity at time 2. And I've already got my v function entered into Desmos, so let me just do v of 2 on Desmos. So let me go down to another entry level, and we'll just do v of 2, not v prime, just plain old v, and that comes out to negative 2.728, which I'll write here. Since the signs of acceleration and velocity are different, since they have opposite signs, that means that our speed is decreasing at time 2. For part B of this problem, they want us to find all times in the interval from 0 to 3 when the particle changes directions and then justify the answer. So we basically just need to figure out all the times when v of t is changing sign on the interval from 0 to 3. And we can definitely figure that out on Desmos. So let me go back there. I already have v entered earlier in there from part A. So let me just zoom in a little bit. Actually, let me just set my interval. And let's see here. Let's make this go from negative 0.5 to positive 3.5, just so I can see a little better. And zooming in here, it looks like there's really only one place, if I click on the function, where we're crossing the t-axis or the x-axis between the open interval from 0 to 3. We don't count 0 because that's not part of the open interval. And it's this spot right here at about 2.507. And that is the only place where we're crossing on that interval. So that means that we're changing direction at 2.507 only.
On this problem, we have Joanna jogging along a straight path, and between 0 and 40 times, her velocity is given by a differentiable function whose values, at least a few of them, are shown in the table here. Okay, and we're told that we're going in minutes, and velocity is meters per minute. So using the data in the table, we want to estimate v prime of 16. Well, we don't know the original velocity function, so we can't directly calculate v prime of 16. But we can estimate the instantaneous rate of change by finding the average rate of change of an interval that 16 is on. So what would be a good interval? Well, we're just going to pick the tightest interval possible. 16 is between 12 and 20 for the times. So I'm going to find the AROC, the average rate of change between 12 and 20. To do that, we've got 240 minus 200 over 20 minus 12. So let's see, that's going to be 40 over 8, which comes out to 5. And that's going to be 5 meters per minute squared. That's what the derivative of velocity is going to be. It's the rate of change of velocity. Velocity is meters per minute. The rate of change of velocity with respect to time. One other thing worth noting on this problem, look at what I did over here. I had my squiggly equals to show that this was approximate. Since I'm estimating a value with this, I don't want to claim that v prime of 16 equals this, because it probably doesn't. We're going to say is approximately equal to play it safe, because we know it's an estimate. For part C of this problem, Bob's riding his bike along the same path. For times 0 to 10, his velocity is given by b of t. We want to figure out his acceleration at time 5. So we just need to take the derivative of Bob's velocity to get the acceleration and then plug 5 into it. So acceleration is going to be b prime of t. We're telling people how we're getting our acceleration here. And that's going to be 3t squared minus 12t. Now let's plug 5 into that. So our acceleration at time 5 is going to be, well, let's see here. We've got 3 times 25, so 75, minus 60. So that's a grand total of 15, and that's going to be meters per minute squared.
For this problem, we are given the height of an object at time t with this h of t function, and we want the height of the object at the instant when it reaches its maximum upward velocity. So we need to find some time and then plug it into this h function. At minimum, we need to do that. So let me go to Desmos and actually enter this h function in there. So here we are in Desmos. Let me just write in h of t equals 24t plus 24t exponent 3 halves minus 16t exponent second power. Okay, so at some point I'll come back and do h of some number. Now, to find that number, we need to find the time at which the object reaches its maximum upward velocity. So it would be good if we had a formula for velocity, and better still if we had a formula for the derivative of the velocity. Well, the velocity itself is just going to be h prime, the derivative of the motion here. So using my power rule, that's going to be 24 plus 3 halves times 24 is 36 t to the 1 half. And then this last one will be negative 32t. Now I need v prime, because I need to see where the sign of v prime is changing. So that's going to zero out this 24, and we're going to have half of 36, which is 18, t to the negative 1 half. And then this will become minus 32. So let's see where that equals 0, and then we can see what the sign change is going on when we get there. So back in Desmos, let me go and graph this out. Let me move this so I can see it. And I can't put prime in there to name an original function. I'm going to call this a of t, because this really is the acceleration. And this is going to equal, let's see, 18t exponent negative 1 half minus 32. And there's what that looks like. Pretty crazy looking. Let me unselect this height function so that's not muddying up the waters here. And gosh, that looks like just a single kind of line going down there. Let me zoom out a bit and see what this really looks like. So that's what's going on. So we have something that can't equal 0 because we have kind of a square root built into it. Well, it could equal 0, maybe, I don't know. Actually, it couldn't, because then we would be dividing by 0 with this negative exponent. So we don't equal 0, and this is just going to cross once and be down here pretty much forever after. So let's go back to this one little spot where it's crossing, and if I click on the function, I can actually get a dot to tell me what that is exactly. 0.316. Okay, so there's a little picture. This is happening at time 0.316 and some change. Now, in order to show that this is the maximum velocity happening at this time, I can't really do the candidates test because this is an open interval, but what I can do, I can say that v prime of t is positive from 0 to this 0.316, and v prime is negative from this spot onwards to infinity. That means that v itself is increasing until I get here and decreasing forever after, meaning this has to be the maximum possible velocity right here. So we just need to take that time now, 0.316 and change, and plug that into our height function. So back on Desmos, let me go down to a new entry level here. And actually, let me go back to my acceleration function and click on that, and I'll copy this. Let me just copy the t value here so I can paste it in later. So now let me do h of the value that I just got, 0.316 and whatever. And that comes out to about 10.264. So the max velocity here, plugging that in, we've got 10.263, 264. Let me call that 264. Actually, looks like they rounded it off to 3. And I guess if you truncate it, you could round it to 3. That type of rounding is permissible on the AP exam. So anyway, that's going to give us choice B.
For number 15, the position of a particle along the x-axis is given by a twice differentiable function x of t. We have x of 2 less than 0, x prime of 2, and x double prime of 2 all less than 0. So which of the following statements has to be true about the particle at t equals 0? Looking at our statements here, these are all talking about whether the particle is moving toward or away from the origin and at a decreasing or increasing speed. So looking at our facts here, we have a negative x and x prime Since those have the same sign, I mean, this is telling us that we are to the left of the origin, and since we have a negative velocity, that means we're moving in the left direction. Since we have the same sign for x and x prime, that means that we're going away from the origin, and that would be true if they were both positive as well. Now, to figure out if we're going at a decreasing or increasing speed, we look at the velocity and the acceleration of the particle. Since those are both having the same sign, it means they're working together. So that means that we are increasing speed. So moving away at an increasing speed, that is going to be choice D. For number 12, we have a particle moving along the y-axis. The graph of the position on the y-axis is shown right here, between 0 and 5 for t. We want to know for what t values is the velocity of the particle negative and acceleration positive. Well, velocity is going to be negative where this original function is decreasing. So that's happening only on 3 to 5. The acceleration is going to be positive where y is concave up. That happens between 2 and 3, and over here between 4 and 5. So if we're looking for intervals where both of these things are true, well, 3 to 5 and 4 to 5, those are kind of overlapping, but only 4 to 5 has the concave up and the decreasing going on. We're only concave up decreasing right here. So the overlap between those is 4 to 5, choice E.